So in this demo, I'm going to present how AI can suggest new collaboration opportunities. So the general idea is as follows. For each pair of authors, we compute a degree of similarity based on their research interests. So for example, you can enter Professor Terence Tao's name and Professor Stanley Osher's name over here. Stanley Osher is also a well-known professor. He's also a professor in math department at UCLA. And you can see their degree of similarity is computed as 0.475. On this background map, Terry is this blue dot and Stan is the orange dot. There are also another 100 authors that appear as these little white dots. So on this background map, two dots are closer if their degree of similarity is higher, and meaning their research interests are more correlated. And two authors are further away from each other if their degree of similarity is lower, meaning their research interests are more separate. So in this box below, we also have the suggested collaborators for Terry. This is done by asking the AI to identify the top 3 people that have the highest degree of similarities to Terry. And the selection is from the set of people that Terry hasn't collaborated before. So now I have talked about how we use this degree of similarity to make suggestions and identify overlapping interests. I will move on to talk about how we compute this degree of similarity. So the way we do that is follows. IPAM has a database that stores its previous participants and as well as the list of papers they published. So we ask a large language model for each participant extract 10 keywords from the list of publications this author had. So over here, you can see the keywords that the large language model extracted for Terry is math analysis, number theory, combinatorics. So, and for Stan, it's numerical analysis, partial differential equations, finite element methods. So it's actually a pretty precise description. So after that, we will tokenize each keyword by splitting them into smaller chunks or smaller subwords. This allows the AI to process those keywords more efficiently. So after we tokenize those keywords, we will send each tokenized keyword into a sentence transformer, and the sentence transformer will create a high-dimensional vector for each keyword. So high-dimensional vector is really just a long list of numbers that captures the keyword's meaning. So each keyword will be corresponding to its unique high-dimensional vector in some sense that has its meaning. So to better visualize how those keywords are, or how those high-dimensional vectors are, we have this visualization over here. So let me enlarge it a little bit. So right now, as we have said before, each keyword corresponds to a high-dimensional vector, but we cannot really visualize a high-dimensional vector. So the way we do this visualization is project each high-dimensional vector down to 3 dimensions and place them on a rotating sphere. So you can see over here, this probability theory, and there's also, you can see the computational fluid dynamics, and you can also see numerical analysis, differential equations. These 3 are pretty close to each other. in this rotating sphere. So, so if you want a more numerical sense of how those keywords are or how those embedding vectors are, you can enter a keyword over here, let's say probability theory, and check the high dimensional vector that corresponds to that keyword. So remember, a high dimensional vector is really just a long list of number. So here it's a list of number that has length 384, and the first 5 and last 5 entries of that list of number is also displayed. We cannot really display all the 384 numbers, so we only show these first 5 and last 5 entries. So after we converted each keyword into a vector, we can reason about their similarities by reasoning about the vector similarities. So the keyword similarities are, below the surface, just the similarity of their corresponding vectors. So inside of this playground, you can select 2 vectors, let's say mass analysis and member theory, and you can compute their degree of similarity. So here is 0.325. You can also compute, let's say, mass analysis and combinatorics. That's 0.261. So combinatorics is less correlated with analysis than number theory. So now we are finished with the way we calculate degree of similarity between 2 topics, 2 keywords. We'll move on to talk about how we compute the degree of similarities between 2 authors. So we still take Terry and Stan as an example. So the keywords corresponding to Terry is displayed on this left column, and the keywords corresponding to Stan is displayed on this red column over here. So for each keyword on Terry's sides, we'll check its degree of similarities to each of the keywords on Stan's sides, and we'll do some computations based on that. So more concretely, what we do is, let's say we start with the keyword of mass analysis, and we check its similarity with every single keyword on Stan's side, and we record the best matching pair. So currently, the best matching pair is math analysis and numerical analysis, and now we have finished every checks, so it turns out to be the initial pair. So their score is 0.61. We will record that score on this plate over here. And we'll move on to the next keyword, number theory. We'll check its similarity with every single keyword on Stan's sides and record the best matching pair. In this case, it's number theory with mass modeling, and their degree of similarity is 0.209. Now we move on to combinatorics. And you can see we're currently checking combinatorics. And finally, it's mostly correlated with this optimization techniques keyword, and their degree of similarity is 0.253. So we'll do that for every single keyword on Terry's side, and let's speed up this animation a bit. After we have found best matching pair for each keyword, we will sort those keywords. Essentially, we'll upweight the keywords that correlate more, downweight the keywords that correlate less. So it's mostly upweighting keywords that are more correlated between 2 sides, and downweighting keywords that are less correlated between 2 sides. We'll do the same on Stan's side, and we will combine those 2 scores and obtain a final score 0.475 over here. So, okay, now let's move on to how the big picture looks like. So over here, you can think about it as a map of these suggested collaborations. Here, the authors are really just nodes inside of this graph, and an edge is formed if the AI thinks these two people should talk to each other, they should collaborate. The colors are just natural communities that arise through these edges and nodes formation. So you can think about it as like natural clusters that the AI think, oh, there should be a community of these people. They should collaborate more with each other. You can also search for a person's name over here. Let's say Terry as well. And you can see his local research neighborhood. So this blue dot over here, let me enlarge it, is Terry. And the green dots are his suggested collaborators. You can see we have Nathaniel and Dimitri and some gonadists. And the yellow dots are 2 steps away from Terry. And the blue dot is 3 steps away from Terry. So in this collaboration sense, they're pretty much friends of friends with Terry. So it's like after Terry has collaborated with these green guys, maybe Terry can think about collaboration with these yellow guys and the blue guy. So it not only show you how immediate ideas might develop, but also how ideas might spread out inside of this network. So that's the end of the presentation. Thanks for listening.